Hello everyone, my name's Christian Catchpole. I'm a software engineer and I live in Melbourne, Australia. First I'd like to say I feel very privileged and to be able to present here at NuttX Online Workshop. And thanks to everyone involved putting it together, especially Alan. So I started my career many years ago writing C++ for Windows applications and touchscreen kiosks and multimedia, and did some web development in the early days of the internet. And whilst I work with web applications these days, my focus has been mainly Java backends, security and highly serious backend systems. But I've always had an interest in electronics and embedded and music and audio and video and all those sorts of things. So as an aside, I've built a few projects over the years, mainly using AVR, and in recent times the Raspberry Pi, and that's got me more familiar with the ARM platform. So I'm also into things such as pretentious street photography and cinematography, with using vintage lenses from places such as Russia and Japan. You're viewing me through a Russian lens right now. And I'm also interested in a thing called Iaido, which is Japanese samurai sword. So without further ado, I'd like to show you a little robotics project I've been working on for the last few years, and until recently it hasn't actually had anything to do with NuttX, but I've sort of found recently that I'd like it to be. So just going to give you a quick introduction to the project and where I've gotten to with the with its basically its port to NuttX. So let's get going. So this is the Juno space probe. It's currently orbiting Jupiter, collecting telemetry and doing some awesome science and sending all that information back to here us on Earth. For most of us, this sort of stuff's out of reach, being involved in these projects in any way. So I got to thinking that I'd like to build some kind of exploration robot that would that could do something cool. But I thought, well, drones are cool. Everyone's into drones at the moment, but they don't really have so much of a aerial drones, that is. They don't really have so much of a range. So that kind of wasn't so interested in going down that path. I could build some kind of ground-based robot, but unless the ability to take that out to some sort of open expanse or anywhere where it could actually traverse the landscape uninterrupted over long distances, not so practical either. Then I realised that I was actually sort of living near the bay here in Melbourne. I just sort of realised that and thought, what if I build some kind of marine robot that can just, swim across the vast expanses of the ocean? And I realised that directly south of Melbourne is Antarctica. So why don't I build something that I can, as a target at least, get to travel the 3,046 kilometres to Antarctica. And I realised that may never happen. I may only make it to Tasmania. I might not even make it out of the bay here in Melbourne, but we're going to give it a go. And as with anything, you work through a series of iterations in what you build. So each prototype becomes more and more advanced, and before you know it, maybe you do have something that can maybe not make it to Antarctica, but do something else that comes along. So what I did is I basically got a Raspberry Pi Model A and a compass module and a GPS module. But before building a water-based craft, I thought I'd test something out on land. So I built a ground-based robot. I'm calling the robots NYX for no other particular reason that I googled a list of Greek gods and found NYX wasn't really being used for any other major projects in the sphere, and it was a short word, and I just decided to use that. So I went to eBay and I bought a solar panel and a little trolley wheel, and I bought some gear head motors. So the simplicity of a gear head motor is you can basically just attach to a wheel to it directly. It's got a gearing mechanism built in. They're just what you call binary DC motors, and they only go sort of, there's no speed control on them. They're just always full forward or full reverse. But for my purposes, this was fine. Some relays, a battery, solar charger. Using a Raspberry Pi means I could just drop a 4G dongle directly onto it for internet connectivity. And in the picture you're looking at now, probably the most advanced piece of electronics there is the 7805 regulator on there, with a capacitor to stop it browning out every time the motor's kicked in. So turning. So as I said, the motors are just controlled with relays, and you can wire your relays in a fashion so that you can send a motor forward or reverse, which means that it will either be driving forward by having both motors forward, reverse both motors backwards, or turning where it will stop and one motor will go forward and one motor will go backwards, and will just basically turn on the spot. So to measure how much distance it had actually turned, I timed how long it takes to do a complete 360, which is 4.8 seconds in this case, and then the maths for basically reaching a target, or technically they're called waypoints. I've just started calling them targets, and is to measure the heading you're on, the target, the angle to the target, which is the heading you'd like to be on. That gives you a ratio of how much angle you need to turn, and then we'll turn the motors that many degrees for that amount of time. So I took it down the park, and at this stage I didn't even have a proper compass module working. So what that means is if you're using the bearing from a GPS module, that's not giving you a proper magnetic compass. That's basically, it's drawing a line through all its last known points of travel, which is fine in a car. Driving down a street, you've got some pretty well defined points of how you're traveling, so you know it knows what angle what heading you're heading on. Over smaller distances, where the GPS point sort of bounces around a bit, it's a lot less accurate. But you can see here that it works. So I took it down the park and I plotted 4 waypoints around corners of a soccer field, and it trundled around, and sometimes it would go off course a bit and recover, but it worked. As I said, the turning not so accurate on grass, different conditions. Even going straight, it's not going to go perfectly straight, but it doesn't matter, because with this system, every 10 seconds it was recalibrating where it needed to be. I wrote most of the software, all the software, in Java basically. I did think it might have been an opportunity to work with a hipper, cooler language, but I could rapidly develop my Java, I think. So I found it a suitable platform for that, and you get all the enterprisey features of knowing that random null pointer exceptions and so forth aren't going to bring down your entire application. Being Java means I can just drop in, such as say the Twitter API, and connect up the camera module, and it can take and tweet pictures directly from the Raspberry Pi itself. There's a control application I have called Mothership, which does mapping and so forth, and you'll see that soon. And basically the same code base for the Mothership, all the code that I've written runs on the device and on the mothership. So all the ability to go to Google Maps and pull down map locations and draw the telemetry information over a canvas is also on the robot itself. So I could leverage the things I was using for the control interface to be able to create nice pictures to tweet from the device. So that worked. So now it was time to start working on NYX 2, which is the marine version. So there's a startup. Well, they're not a startup anymore. They were at the time. Blue Robotics. They bunch of young guys who were interested in marine drones and marine applications, and they found that marine thrusters, not being the most highly sought after devices in the world, were actually quite expensive. Found they were made from, most of them are made, steel-based products and things that actually weren't compatible with the ocean so much. So they designed and built the T100 thrusters, which are mostly plastic, apart from the motor coils and some of the mounting hardware, which means that they're light, cheap to produce, water cooled. Don't need any fancy cooling mechanisms because they're basically underwater, and they'll run over 100 watts, I believe, and can produce quite a amount of thrust. So the other thing I was going to need, as soon as we get a 4G range, is to be able to communicate with satellite. So I've also started working with the Rock Block. So Rock Block have taken a standard Iridium satellite module and packaged it up and provided that. So how does the steering mechanism work for the marine version? It's very similar to the ground-based version, except that the thruster controls aren't binary, and we're not going to proceed in a straight line for 10 seconds and then readjust turning. We're going to be constantly adjusting the left and right power, which I'm calling the left and right power of the thrusters, to create a relative balance of powering on the left and right of the vehicle to push it from one direction to the other. I've had all sorts of criticisms of my design and people saying I should use rudders and so forth, but this works. I've got this working. Works quite happily. So we have a thing called an impulse power, which is your base power level between 0 and 1, and you scale that to the amount of power you're sending to your thrusters. And so if we want to steer towards the target, which is sort of to the right there, we need to push the left side over. So the left thrusters will have more power and the right thruster will have less power relative to the impulse base thrust power. So this was it in action. So this is the first iteration of NYX 2, swimming around in Port Phillip Bay. The design's changed a bit since then, but fundamentally it's a foam board with a solar panel and a battery, and a compartment for the electronics. I used just some basic plumbing parts there. I used a tube with sealable ends, which I thought was a great idea at the time, but found it's actually really hard to just get in there and work with that. So that doesn't work so well. So things have changed since then. And in this instance here, they've just got a small battery just sitting on top of the robot. I've changed the design since then, where I used the battery actually as a keel, as a weight underneath, which battery's got to go somewhere, so it may as well be underneath the water line to keep the weight down. Use it as a keel. Here's a picture of it hitting an epic wave. Very soon after this photo was taken, it actually flipped upside down, took on water, and we went home for the day. But I just found that one of the Raspberry Pi had got some salt water on it, which had killed it. Pulled one out of the drawer, swapped it out, and we're back in action. So this is the next iteration of NYX 2, which slightly more Star Trek design. Used a special container box that has cable glands to get the wiring in and out of the sealed container, which can be easily opened for maintenance. And this is a picture of it sitting on dry land with the battery keel. Not so hydrodynamic. The whole design is not particularly hydrodynamic. It should be built more like an actual boat, but I'm not in a position to really do that. So this is where we are, and this is what I've done, and it's something, and it works. Yeah, so here's the sort of the mess of electronics inside. So it's a bit of solar charger, and you can't really see it there, but there's a Raspberry Pi buried down there with bits and pieces. Okay, let's take a look at the Mothership application. So this is a Java application which is used to control the robot, and in this case we're actually going to be playing back telemetry that we recorded from a mission. We're going to play back the telemetry much faster than real time, otherwise we'll be here all day. You can see the clock in the bottom left hand corner, the second hand spinning around much faster than usual. We've got a square up in the corner which goes green when we receive telemetry and turns red if we don't receive telemetry in a few seconds. It's very helpful to just see at a glance whether everything's okay. So we can see here that the robot's been taken out into the water, given a selection of waypoints or targets to swim through, and it's happily doing that. See the bearing measurements and its steering. Take notice of the speed kilometers per hour. That's an estimate that's calculated by the Mothership. So when we're playing back at much faster real time, it completely loses its mind. So you'll see there the left and right thrusters proportionally going up and down to steer the craft, and then we've also got battery level and voltage levels. So there's 4 of those there because there's 2 pairs, because they were using a version of the thrusters which were actually providing that information, so we were able to log both of those at the same time. So the robot will happily just run through those targets all day in calm water. It's been very successful. So quickly we'll show you the couple of the more advanced algorithms, if you call them advanced. Hold position. So the idea of hold position here is if you want to shut down for the night, or for some reason just want to hold a position, but of course the current is drawing the craft away from that position, we'll set an inner radius and an outer radius. If the craft floats outside of the outer radius, it will swim back to the inner radius. The benefit of having 2 rather than 1 is if it was 1, it might constantly just be trying to tick over back over that line, whereas having 2 means it'll use a bit of power to get back to the inner radius, but then we'll be able to drift back. The other one is hold position and track to target. So if we're powered down for the evening, or for whatever reason we don't have much power, but we are still heading towards a waypoint that is further away, what it will do is it will allow the craft to drift in that direction. So as long the hold position target is basically constantly being brought towards the waypoint if it's floating, if it's become closer rather than further away. So you can see here that this sort of creates this odd pattern where it will under power, for short amounts of time, stay on track and let the current do most of the work. Here are a few pictures with overlaid maps and telemetry. So what's this all got to do with NuttX? So as I was developing NYX, I started developing a Raspberry Pi hat. So that would bring all the devices together, and with my experience with the AVR, I thought that I could move a lot of the I/O and some of the hard real-time requirements to the AVR, meaning the Pi could just be higher level planning, and that basic navigation and return to base and emergency phone home via satellite and all that kind of thing could be done through the AVR. So I was kind of struggling a little bit to get all that capability into an AVR, but then this thing came along, the Sony Presence ARM-based, NuttX-based IoT board. So I started, obviously because I had the board, I started playing with NuttX and was having a really good time with that. So I've put together a demo of some of the core functionality that I've moved from the Java NYX to NuttX NYX. And for the demonstration purposes, I'm not going to use Sony's Presence, even though I'm sure it's perfectly capable of doing that, more so than this board actually. So what we're going to use here is an STM32F4VE board, which is, as far as I can tell, pretty much basically compatible with the F4 Discovery. So what we've got here is the STM32 board itself, a GPS, ESP12F Wi-Fi. So this is a board here that I've made with an AVR to drive the ESP. But I've just populated the board just enough to basically get the UART connected to it. Got an extra power supply here. This is because the ESP can use quite a bit of power, so we're just going to make sure it's well powered. So that's now 3 amps power supply. And we've got not to leave the Raspberry Pi behind, we've got a Raspberry Pi here on the left to allow us to connect to the NuttX shell. And you'll probably recognize the ST link there in the corner. So this is basically the system. See if I can rescale this a bit, see it a bit better. Okay, so this is the basic architecture of what I have so far. I'm not claiming it's actually the best architecture, it'll probably evolve, but this is the point I've got to so far. And I've used green circles and red circles, one to basically represent where there is a P thread in action, and the red circles are what is not currently implemented for the demonstration. So we have a thread polling GPS, a GPS in preference would be set to 500 milliseconds, but for our demonstration purposes we're going to use the default of 1 message per second, and the compass. So in practice we'd be polling a compass module 100 milliseconds or more, or sooner, but for demonstration purposes about 250 milliseconds. And then the other thing is the GPS. The GPS is going to, on the first time it receives a time, it's going to set our system clock using GPS time. So these are going to create telemetry messages that we put on a telemetry queue. The telemetry queue is going to be read by a routing process. And the purpose of the routing process, as you can imagine, is to it doesn't do too much actual hard work in that process. It wants to pull messages off the queue as quickly as possible. So it's going to send a copy of everything to a broadcast queue. Purpose of the broadcast queue, as you can then see, is going to send to an ESP sender. I've written a basic, probably wouldn't even call it a driver, just a simple implementation to send messages to the ESP Wi-Fi module using Haze AT commands. The benefit of that module is that you can just use simple commands to send UDP packets and open TCP sockets and so forth without requiring a full TCP stack to implement that. Of course, being single-threaded, but that's all we need in this case. And also, what we don't have implemented, but on receiving of pings, if we get ping messages back from our mothership to tell it that it's actually listening, those ping packets would be fed back into the telemetry queue. Underneath here we've got the satellite modem sender. The idea is that a UDP sender is going to send every piece of telemetry it receives because they're cheap and quick to send, whereas a satellite modem receiver may collate them up and send them every 30 minutes or average them or decide however it wanted to send those packets. The other advantage of UDP in this case is that opening a TCP socket and negotiating it and keeping it open and making sure it doesn't time out isn't something that is exactly preferable if your network is a bit dodgy, robot, be it on say Wi-Fi or 4G reception is patchy. In this case, we don't whilst we would prefer to receive every packet, it's not the end of the world if we don't. So this is sort of the simplest, surefast way to get consistent telemetry without having to rely on a process that will watch for timeouts and try to recover from those situations. So coming back down to the routing process, the routing process will also send every piece of telemetry to what we're calling a snapshot queue. The idea of the snapshot queue is that it won't send every piece of telemetry to snapshot queue. It will store the best known state of each class of telemetry, so that the snapshot is the last known GPS, the last known compass, the last known whatever piece of state that the autopilot process will then process. The idea of having that autopilot process as something that is fed simply a snapshot is this is basically a functional approach in that can be decoupled from however that telemetry made it to that queue, and can, as per the demonstrations of the replay, be replayed, simulated in non-real time. In preference, the snapshot would also, the time information, the autopilot process would not go to the system clock to find out what time it was. Time would be placed in the snapshot so that it works in a pure way. And then finally, the result of this is going to go to the thrusters, and we're also going to be broadcasting the state of the thrusters and the steering information to the broadcast queue so that the mothership and any telemetry logging can observe that. So let's fire it up. So I've got the nutshell here connected to the demonstration. So we can see TTY S0, 1 and 2, so that's the NuttX shell, the ESP and the GPS. And in proc we're going to be also using CPU load and mem info. So I'll just start up our local instance of Mothership here. So it's red, waiting for telemetry information. Mashi is program name. Wi-Fi disconnected, Wi-Fi connected, and away it goes. I'll explain what all that logging means in a second, but let's just see what's happening here. We can see here it started on a heading of north and it had a target to reach down here. Immediately turned to head to that target and is swimming towards it. Time, real time here, bearing, steering, thrusters. Again, kilometers per hour. In our simulation it is traveling 15 kilometers an hour. Doesn't quite go that fast in reality. So how's this working with a real GPS? What I've actually done is the GPS data is real, but my GPS isn't moving. It is slightly skewing, slightly giving, slightly, changing points as it sits here in my window, not with a clear view of the sky. But of course, I'm not in the bay. I'm a few kilometers inland. So what I've got the GPS to do is, the first time it reads a location it's got a pre-stored location to the middle of the bay, and it subtracts the actual location from this predetermined location and uses that as an offset. And then the simulation is also going to, as the craft swims around, move the simulation GPS coordinates relative to where it thinks the craft should be. Let's have a look at the logs here. So I did have a just standard printf logs going. So what I decided to do is I made this little collating system here. Each log event is given a source, instance, and action. All of those are expected to be constant strings, or at least ones that aren't moving in memory, so that on subsequent call it will remember those pointers and account for that kind of telemetry, and then on subsequent calls it will look those up in the table of the row and know what row to repaint over. Of course, any new message just goes to the bottom. So first telemetry instance here, count 1. So we've only received one log call of time, the system start time. Max headroom here is a printout of our largest telemetry size, which is basically the snapshot message. CPU sitting at 5%. This processor runs at 8 megahertz. And memory seems quite stable there. We created 4 threads as we started up the AT session. We're logging here commands sent to the ESP, so we can see here these basically are UDP packet sizes. The telemetry queue is sending and receiving telemetry. You can see that number 8, 8 and 12 bouncing around. That's basically currently our two kinds of telemetry in this example, which is a heading and a location. Location heading being one floating point number, and our location being 2, and the class also has a vtable. We're going to talk about that a bit later. Snapshot queue, routing. So as the routing process processes each kind of telemetry onto the snapshot, it logs it out, and what you're seeing here is JSON, and that's basically because the serialization method that we've used for telemetry is JSON. It just makes it easier to process on the Java side, easy to read and so forth. Next event that came along here in time was the broadcast queue. You can see the messages going to the broadcast queue, so they're basically being picked up by the mothership there. GPS clock set, that's where it's set. This is in milliseconds, so this is where it's set the system clock. GPS coordinates here. These are the offset coordinates relative to my house plus the offset to the position in the bay. And snapshot queue always sends and receives the same kind of size. Autopilot, so the autopilot process, which is steering the craft around, is showing, we can see here there as it's swimming to its target, the heading the craft is actually on, its expected heading, the steering, which is a positive, negative to 1 of steering value, and then the relative left and right thrusters. So you can see these numbers here reflected basically down here as they arrive. Snapshot queue, broadcast queue, sending, and the ESP sender. So this blast log item here is every piece of telemetry being sent. So how have I implemented this in code side? So I won't go through every line of code, but I'll just try to give you a basic gist of how I've structured things here. please don't point out my inappropriate use of char pointer casts, and I've been writing Java for a long time, so probably see that style creep into my code style. But you can see here that I've created wrapper classes around things to make them convenient to use, and so that the core implementations of functions end up being quite small because everything is wrapped up in classes further down. So we can see the ESP sender here, how it just basically initializes the ESP12. A few bits and pieces commented out that aren't needed. Same with the GPS, using the GPS parsing library in NuttX. If a clock's not set, we get the clock from GPS information and set that, and then that's also a good opportunity to set our offsets for the lat and long for and when we further pick up locations, we'll offset those. And let's have a look at, so it's basically the main method here. Set up GPS, set up our telemetry queue, broadcast queue, snapshot queue, routing process, given it a thread, ESP process, give that a thread, sensor process, and then the autopilot. And by abstracting all these things into these classes, it means that this main block here is how we create a system and wire it together, which allows us to, say, create different robots that have those different components put together, or test scenarios as well, where some of these classes are substituted for simulations or connected in different ways. The GPS, read from the GPS, send to the queue. Quite a small method there. And up to the routing process. So this got here, we'll call it telemetry union. So of each kind of telemetry we have, I've created a union which means that we can receive the largest type of those, and then by selecting on its type, which are enumerated properties on virtual methods, we can set in the snapshot the last known good state. These are the logging messages here that I was describing earlier. And then in this case, we're going to send data to the snapshot queue when we receive a location. This suits the example that I'm demonstrating here. In reality, we could do that on the receipt of any piece of telemetry state. We could check whether the autopilot is actually busy at that time, has any free message queue space, or is actually busy. So we could decide when to send, or so as to not overload that system. There's all sorts of options here. As I was testing my NuttX implementation, I left a simulation running overnight, and I found in the morning that it hadn't reached a target in a very long time. And I thought, I just must have some fundamental bug in one of my algorithms. But what I found is the way I'd configured the sharpness of turning and the stepping of distance was that it had gotten a situation where it couldn't turn in fast enough to actually reach a target. So it was just going around and around and around and around. And then I realized, if you consider forward thrust as momentum and the turning angle as the force of gravity, I actually here created a planetary orbiter, just like Juno. So that was a brief overview of my project and where I've gotten to with NuttX. It's been quite good, actually. I think I've achieved quite a lot in a short amount of time, and I'd say I hadn't really been learning NuttX at all, because they're all standard APIs that systems that I'm used to. So there wasn't much to learn. other than say configuring a system using the kconfigs to get the best out of system, and really impressed by the way that works and how easy it is to just switch things on and off and configure a system. So yeah, anyway, thanks for everyone's patience with my rambling for the last 40 minutes.